Okay, let's get started. So it's a pleasure to welcome our last speaker of this morning's session. It's Gerhard Rosenberger, who was a long-term collaborator of Ben Fine, and he's going to tell us something about a mathematical life with Ben Fine. Gerhard, please.
Thank you very much. You just mentioned the book of Ben Fine. One of the books, I have it on my desk. It's called Out of Granada, and it's published in Symbol House. Okay, that's for the introduction. Thank you very much that I may speak here. The first time I met Ben, 1983 in New York, so we have 40 years collaboration, and he asked me about a little note with Norman Podsitzky. At that time, I was concerned mainly with automorphic forms, analytic number theory, just finished classification of two-generator Fuchsian groups, worked with Zishank and Beksinski on the rank problem and minimal generating system for Fuchsian groups. And the note with Podsitzky was just a little byproduct. And I was a little bit upset because Ben did not know about all the other things and all the other results. So he did not give up and came to me and asked me, and we talked and talked, and we started to work together. First in complex analysis, the result were two books in Springer on number theory. I just mentioned a little thing of that. The Klein-Fricke groups are the groups with this type of my matrices, where the square roots are of n are the diagonals, and the matrices of the first type generate a subgroup, a normal subgroup of index 2. And if you conjugate any element with, or if you conjugate T with any element of the group, then you get a matrix of this form. So what is there? You see x squared plus y squared. And the question is, how can we use it to describe numbers of the form x squared plus ny squared? We have to ask for the conjugacy classes of Gn of elliptic elements of order 2 in this coset Thn, the cosets Thn. So we got the following nice formula. The number of conjugacy classes for epsilon n and the class number of minus 4n. And the epsilon n is given by these values here. And if you take just the case n equal 1, then we automatically have the number of conjugacy classes is 1. And there, if you have greatest common divisor of x and y equal 1, then n is a sum of squares if and only if minus 1 is the quadratic residue modulo n. This is just Fermat's little theorem, so it's an easy proof of that. And we can do many things for bigger n's. For instance, if the class number is less or equal 2, and the first complicated case is n equal 11, and that we completed with Martin Kreuzer. So related to all these considerations is the theory of arithmetic Fuchsian and Kleinian groups, and Ben and I started to work with Colin McLaughlin and others on these subjects. One of the results is, just to mention it because I like it very much, we got the complete classification of all arithmetic-oriented Fuchsian surface groups of genus 2. And in fact, our main work started in the midst of 1980s, so say 1986 or so. And Ben and I had two different ideas. The first idea was we started to work with T-Shank's results or Nielsen cancellation methods in free products with amalgamation. And we refined this method and used it for the rank problem, the classification of minimal generating system, the N-free question, equations in several classes of groups, like free products with malnormal amalgamated subgroups, one-relator groups, like cyclically pinched one-relator groups, conjugacy pinched groups, and certain para-free groups. From this side of, there is a little result in the third is nice. It's concerns with the London type equation x square y square is equal 1 in the group. And, we had one relator group, say with the relator R, and with torsion. And then the following are equivalent. G is conjugated separable abelian. G is an RG group. G does not contain the copy of the infinite dihedral group. And if you have in G the equation x square, y square, z square equal 1, then the subgroup generated by x, y, z is cyclic. Just to remind the definitions, CSA means maximal abelian subgroups are malnormal, and RG means if G and H are elements, then either the subgroup generated by them is cyclic, or there is a big power, and we have a free product of two cyclic groups. Another result, by the way, using Nielsen transformations is the classification of fully residually free groups, limit groups of rank less or equal 3 together with Tony Gaglione, Alexei Myasnikov, and Dennis Bellman. Now our second idea. The second idea came from Ben. We met at a meeting, I think it was in St. Andrews meeting, and he came up with the question, what happens if you take a one-relator quotient of free products or free products with amalgamation or so on? Especially he was interested in the case of one-relator products of cyclics. That is groups of this type of presentations. And the result was, together with Jim Howie, we got in what we called essential linear representation in the following form. There exists a homomorphism of the group G in the PSL2C such that the subgroup generated by the first n-1 generators injects into G and via rho into PSL2C. And the image of the relator has order M, exact order M. So in the most cases, we could use these linear results to find that G has satisfies the Dietz alternative, is SQ universal, virtually torsion-free, and which allows to give a rational Euler characteristic, or we could write G as a non-trivial free product with amalgamation. And now I will mention our work with Gilbert Baumslag. For both of our ideas we had, there was an overlapping with work of Gilbert. First, I had a big paper on groups whose free generator subgroups are free. Exactly a paper with the same title at Gilbert Baumslag with Peter Schalen. And secondly was we had the work with Peter Schalen and John Morgan, the Baumslag's work with Peter Schalen and John Morgan on generalized triangle groups. So this was a starting point of our common work with Gilbert Baumslag, which also led to the common book, a course in mathematical cryptography with Martin Kreutzer. And at that time, in fact, it started a bit earlier. We wrote a paper on N-free groups, but the collaboration with Tony Gaglione and Dennis Spellman on different subjects of groups and model theory for groups and group rings and finiteness properties in infinite groups intensified, leading to the paper on some finiteness properties in infinite groups with Gilbert Baumslag and Oleg Bogopolsky. And also in the book with Alexei Myasnikov on the elementary theory of groups. I now want to mention what I believe is Ben's most favorite conjecture, that is a surface group conjecture. And I like it in the following way. Suppose G is a non-free, non-cyclic one-relator group such that every subgroup of infinite index is a free group. We call that property IF. Then G is a surface group. This conjecture is still open, but together with Laura Siaboni, Olga Kalampovich, Alexei Myasnikov, Vladimir Mesnikov, we got partial results. For instance, the surface group conjecture holds for finitely generated, fully residually groups with property IF, or cyclically pinched one-relator groups, conjugacy pinched one-relator groups satisfying property F. And G is either free or a surface group. So there are some classes where the surface group conjecture holds. Unfortunately, it's still open. There's many things to do. And lastly, I want to mention Ben's, what I believe, favorite groups, that are the groups of F-type. A group G is of F-type if it admits the presentation of the following form. We have generators, A1 up to AN. In the middle, you stop with the P. And you have words of infinite order, U and V, and the product is equal 1. The U is in the first generators, and the V in the second generators. And that we call the groups of F-type. Together with Ari-Juhasz, or especially Ari-Juhasz was the main part of this proof, these group of F-types are hyperbolic if not both U and V are a proper power or a product of two elements of order 2. That's not really surprising, but we have at least a classification of the hyperbolic groups. And if we use our techniques, which we had in the earlier papers, then we automatically can say that G is hyperbolic if and only if G has a faithful representation in PSL to C. That is a typo. It should be PSL to R in the real. Certainly, it's not correct if we take the complex numbers. You see the infinite dihedral group and the group generated by 3 elements of order 2 can be presented in the PSL to C, but not in PSL to R. So this is unfortunately a little typo, must be R. So again, let G be a group of F-type, then G is hyperbolic if and only if G has faithful representation in PSL to C. So we got many results and properties for groups of F-type. I will not mention any more, but I just want to mention a last result. It's related to the surface group conjecture. let G be a group of F-type, which is not a free product of cyclics. Suppose that each subgroup of infinite index is a free product of cyclics. Then G is a co-compact planar discontinuous group. Well, that's very, very much related to the surface group conjecture. In this sense, this result closes the circle to the beginning of Ben's mathematical work. It's his last result in his last paper together with me and Leonard Winke. That's the end of the story. Maybe I should mention one thing I forgot to mention at the beginning of my work, Frank Levine and Benjamin Baumslag. I worked together with both of them, and I think I'm one of the few people which have a paper with Gilbert Baumslag and with Benjamin Baumslag. And that's quite good. So thank you very much.
All right. Thank you, Gerhard. Very
Unfortunately, I could not manage that you see. So on my picture, I don't know how could I do that?
That's all right. If there are any questions for Gerhard or comments, so you're welcome to speak up. I had a question. It was a little too fast in the for formulation of this surface subgroup conjecture, or what was it? Surface group conjecture. Was the requirement on all finitely generated, on all subgroups of infinite index, or only on finitely generated subgroups of infinite index that they are free?
These for the surface group conjecture, the subgroups of infinite index have to be free.
All subgroups, including the ones which are not.
Yeah, yeah, not finitely generated.
I see. So this is.
And I mean, there are many versions for the surface group conjecture. Another version is subgroups of finite index are one-related groups, and subgroups of infinite groups are free. I think the second condition is more important than the first condition. And it should be enough only to force that subgroups of infinite index are free.
Okay, thank you. All right, are there any other questions or comments? So if not, let us thank Gerhard again. Thank you. So let me stop the recording.